Hello everyone, we are May. So today we would like to have one special guest here. Name is Dr. Muhammad Sabit Aiman. He just graduated from School of Material Science and Engineering in Yttrium University. Could you please introduce yourself?
Oh yeah, sure. Thank you first of all, thank you for inviting me here, May channel. And as mentioned, my name is Muhammad Sabit Aiman. I am from Indonesia and I just graduated and I took my master and PhD degree here in Yttrium University, Material Science and Engineering. And I focused my research during my master PhD on fabrication of transparent ceramics. And now I'm doing a postdoctoral position here. And yeah.
Wow, that's quite interesting. Transparent ceramic. What is that? Can you talk more about this?
Yeah, that's a good question. So I want to ask you, what is on your mind when you think about ceramics?
Ceramic, usually like porcelain or earthenware or like pot for our flowers, something like that.
That's usually what comes to people's mind when they think about ceramics. And let's see on this image here. And so when we talk about ceramics, usually we think about earthenware, porcelain, and many other daily use items. But maybe many people do not realize that or do not know that ceramics can be transparent also. So we can see here, this is a
normal ceramic.
Yeah, common ceramic, glass ceramics. And here also ceramic, but usually people call it glass. So do you know what can make ceramic become a transparent?
That is what we want to know from the expert.
Sure. All right. So if we see on this schematic diagram here, so you see here, this is a ceramic, transparent ceramic, and
how it's so transparent.
Yeah. How can it be transparent? It's just like a glass, right? So if we see on this diagram, this is a band gap energy of different materials, and we see
the
here
first one is metal.
Yeah, as you know, and semiconductor and insulator. So do you know what's difference on these three different materials?
The first one, metal, there is overlapping between conduction band and valence band.
Yeah,
in the middle, no, and then insulator, they are very huge gap.
Yeah, correct. So these properties of materials is the most basic and fundamental on how a material can be transparent. So to be a transparent ceramic, a material should have a very large band gap energy here. You can see compared to the other two, semiconductor and metal, they have like very little or none or overlap band gap energy. So how it makes the huge band gap energy makes a material transparent? So we can see here on this figure, and we can see that if a material have like non overlap or very little band gap energy, less than 3.26 electron volt, that it cannot transmit light here. So it will be
just reflect.
Yeah, either reflected and absorbed. But if a material has band gap energy higher than 3.26 electron volt, then besides the reflection, the light can be transmitted here.
What kind of light, Dr. Aiman? All types, all wavelength, or?
Yeah, that's a very good question. So usually when we talk about transparent ceramics, usually we talk about visible light, which has a range of 380 to almost 800 nanometer, which equals to 1.55 to 3.26 electron volt. So let me explain more here. So we have a schematic of like here is a valence band and here is a conduction band. And when a photon like has an energy higher than the band gap energy of a material, then the photon will be absorbed by the electron in the valence band, and then the electron will be excited to conduction band, and then it will relax again, come back to the valence band. So in other words, the photon will be absorbed. It cannot be transmitted. But here we can see there is a very huge band gap energy of material. Then the photon has lower energy than the band gap energy of the material. So the photon doesn't have enough energy to excite the electron from valence to conduction band. So it cannot be absorbed. So rather it will be transmitted. Why the band gap energy should be higher than 3.26 electron volt? Because the higher energy of the visible light wavelength is 380 nanometer, which equal to 3.26 electron volt.
So the threshold will be 3.26 electron volt.
Yeah,
and
correct.
it's belong to the violet.
Yeah, kind of violet. Yeah.
Okay, that was interesting.
Okay, so besides, like we already talked about band gap energy, which is the most fundamental characteristic of a transparent ceramic, then there are also other factors here. So first is the isotropic crystal structure of the ceramics or the material. So we can see here two different crystal structure, non-cubic and cubic. So in non-cubic crystal structure, the light will be scattered at the grain boundary. Here you can see here is grain boundary, and light will be scattered. And why is the reason? It is because the non-cubic structure has different refractive index for different planes orientations. So therefore, because
How it has different refractive index?
that's just the intrinsic characteristic, I think, of the like non-isotropic or non-cubic structure. So for all the orientation, it has all different refractive index. And on the other hand, for the cubic structure, it has all the same refractive index, just one refractive index for one material. So there is no scattering at the grain boundary, and the light can be smoothly transmitted.
How if we have like very fine materials, but the grain boundary density is so high? Will it like change the scattering behavior?
Oh yeah, that's also a good question. So let's see on this figure here. I have this figure. So this is an incident light, and all materials will some of the light will be reflected here, you can see, but for a transparent ceramic, most of it should be transmitted here. So, and we can see some diffuse transmission here. So diffuse transmission is usually because, like, you know, the roughness of the surface of the material. So it cannot just smoothly transmitted, but slightly transmitted into like little bit different directions. But that's because of the surface roughness. So the smoother the surface, the smoother the transmission of the light will be. And we can see that the light band because of the refraction phenomena here. And when there is pore here, see?
Oh yeah, pore. Usually we find pores in our materials.
Yes, correct. And especially for ceramics, it is very difficult to get a very dense microstructure. So therefore, it should be minimized, the pore in the transparent ceramics. And when the light meets the pores, because
It should be air, right?
yeah, it is air. So
refractive index should be
yeah,
different.
it's different. Correct. You get it very like fast, and because of the different refractive index, then it will be scattered here. You can see into many different directions, and also besides the pore, another phase or secondary phase, besides the phase of the transparent material itself, it also has refractive index, and therefore it can scatter also the light. And also depending on the material, it can also absorb the light here. And after that, it will be reflected again once more at the bottom surface of the material. So there will be 2 reflection here. Then in the end, it will be transmitted. So the point here, pore should be minimized, like maybe like 99.9% density is
Wow, it's
kind
so
of preferred.
dense
Yeah, it's very difficult to
achieve. Yeah.
to sinter and fabricate transparent ceramic. And also we should have like very high purity of the material, so like impurity or second phase should be avoided.
Understood. And what is more interesting is here you talk about cubic and non-cubic. So it's about the properties that they are isotropy and non-isotropy, right?
Yeah.
If they are non-isotropy, means they can be generating different properties in different directions. So we should avoid.
Yeah, so it's very difficult to use a non-cubic structure of ceramic as transparent ceramic. But although there are some like quartz for silicon dioxide and sapphire for alumina, but they should be fabricated into a single crystal material to be a very highly transparent. And that's why it's generally just easier to use cubic ceramic for the transparent ceramic, because it's like cheaper and simpler to fabricate. Yeah, like that.
Wow, thank you for the explanation. Oh, wow, what is that?
Okay, so I want to ask you something. Can you guess or distinguish which one is glass, which one is ceramic?
It's almost look the same like everyday glass. I don't know which one is ceramic, or is it like glass part of ceramic?
Yeah, so by appearance, it's very difficult to tell which either is it like glass or ceramic. But what I want to tell you here is, like, usually people get mistaken. They think glass is different from ceramic, but actually glass is kind of part of ceramic. And we know that ceramic is like a material that has like ionic and covalent bonding that is very strong, and usually composed of like cation and anion. And but what I want to tell here, glass and ceramic basically can be the same like material, the same chemical compound, but it's the structure that differentiate that we can see here. This is glass and this is ceramic. And can you tell what's different about that?
The left one, so it's for the glass. It looks like not well structured. The pattern is a little bit, how to say, not well arranged. But on the right side, it is so beautiful because it seems to make perfect pattern, like high symmetry, like that.
So yeah, correct.
So here is glass, and on the right side is ceramic. Is it correct?
Yeah, because I got the image, so I know the left side is glass and the right side is ceramic. But yeah, as you explained that, the structure of the atoms and the order for glass, it's just basically like a disorder or very low degree of orderness. And for ceramic, it's very well like ordered and structured, so it has like crystal symmetry. So we call it like crystalline, and for the glass it's amorphous.
Amorphous and crystalline. What happen if we like how to say, drop this kind of material from high position to low position? It would directly break, right?
Yeah, generally like both glass and ceramics, they are quite brittle, I would say, and much more brittle compared to like metal or polymer or other like materials. But yeah, depending on the materials, they have quite different properties in terms of mechanical properties. Like the hardness, the strength, and the toughness can be quite greatly different depending on like each material. Now let's see like some common types of glass, and I'm sure you're familiar with this borosilicate glass. Like so, it's usually used for
experiment.
Yeah, correct. In laboratory, and usually they have kind of like specification for use in temperature like up to 200 degrees, something like that. And depending on the glass, like usually it's kind of dope or like added with like
impurity.
Yeah, kind of different, like in this case is boron and silica. And for different glass, like this one is soda lime, is sodium and calcium oxide. And like depending on the application and the purpose, they can use different materials for doping, but basically it's based on like silicon dioxide material.
The soda lime we usually use for like soft drink or
Yeah,
soda
correct.
drink,
Beverage like bottles. Yeah, because it's like generally cheaper and doesn't require very like,
high durability.
Yeah, high temperature use, something like that. And this is the least common type of glass.
The least common
in this figures, and it's added with aluminum oxide, and we can see here that even it can be used for like a foldable phone for its screen. So yeah, like depending on
the screen made of aluminosilicate glass.
Yeah, based on the information from the website, can be used.
Oh, that's
surprisingly
interesting. Okay, we talk a lot about glass, transparent glass, and could you let us know more about transparent ceramic?
Yeah, sure. So we've talked about glass. Now let's dive into some of the most popular transparent ceramic, I would say.
Yeah, I know that one. The first figure.
Yeah.
It's from one of the most memorable movie, Jurassic Park,
yeah,
right?
Correct. That's correct. So, although I do not have information whether this, so I want to talk about this. What is it called? Gyrosphere.
It's like capsule.
Yeah, but technically it's called gyrosphere.
Gyrosphere.
It's kind of type of vehicle, like modern looks like that. And although I don't know about in this movie, like what kind of material it's used, but this aluminum oxynitride or Gamma AlON, it has very superior mechanical properties that usually people use for like blast protection window, for like kind of bulletproof window.
Oh wow.
So that's why I show this picture, because in this movie, like it should protect them from getting
all kind
attacked.
of debris from
or
air or atmosphere.
Yeah, or even getting attacked by the dinosaur, right?
Oh.
And besides aluminum oxynitride or Gamma AlON, we see here it is called magnesium aluminate, or people usually call MG spinel. Because it has a spinel cubic structure. And we can see here that it can be used for the like dome of the missile. Yeah.
Missile? It's not camera?
No, it's not. It's a missile, like missile for like military purpose. And here is the enlarged image, and you can see here that it's like a dome shape, and it's just basically a like window, a transparent window to transmit the infrared light. So it should be transparent in the infrared region.
I see.
And as I mentioned, that even like non-cubic structure can be transparent, and this is the example. It's single crystal sapphire. It's basically aluminum oxide material, but it is very well like oriented We can see here.
Is it man-made or natural?
Yeah, it's synthetic.
Synthetic.
It's fabricated.
But I guess to make this one need like lot of cost due to the like difficulty and etc.
Correct, you're correct. So there are some methods to fabricate this single crystal material ceramics, but it is very costly and difficult, like
so
complex.
you suggest to make with polycrystalline instead of
Yeah,
single
yeah.
crystal.
It's just generally like easier and cheaper, although it's not easy at all. Okay, and another one is yttria here. See?
So for military purpose again?
Again, yeah, there are many kind of application in military area, and it's used for this lens, like what is it called? Like
It's for zooming, like zooming out, zooming in.
it can be, but it's like night vision, like night vision camera. So see, even though it's like dark, but you can see here people and hear people, because like object, especially like living creature, they have some heat in their body, and therefore they transmit the heat in the infrared wavelength. So by using like night vision device, you can see like the shape of the object that transmit the heat, and it use the
This use like infrared capture or what kind of, like basically the normal person without these materials they cannot see, right? Only that person can see.
Yeah, correct. Only that person. So it can be recording if it's camera or just a device to see in the dark environment. Yeah, but it require like lens that is transparent in the infrared wavelength. So yeah, yttria can be used for this purpose. And although yttria and it's like kind of, I would say like some kind of brother. So it's yttrium aluminate. So it's a mixture of yttria and alumina, and make like different another new material, which is yttrium aluminate, and people usually call it yak.
Really?
Just because of like yttrium, aluminum, garnet. Like,
garnet, okay.
And usually they dope with some rare earth elements like neodymium or like ytterbium or erbium to give some like optical characteristic, which is like absorbance and also more importantly photoluminescence behavior. So later on,
so it's depend on the application, right?
Correct, but generally it can be used for laser application.
I see.
As of like laser cutting, or surgical laser in medical.
In that case, the yak or yttrium aluminate garnet usually more expensive than the brothers?
Depending on the
final product.
You have material cost and fabrication method, or the kind of more advanced application. Yeah, it can be more expensive. Okay, and
this is the reason why they are having different properties, right?
Yeah.
Because
so can you see here in this figure? The glass held by hand.
Right.
It's very transparent.
So transparent that you can see what is behind. Is it pyramid?
Maybe just a building. And I want to ask you, can you guess what's the transparency in terms of like percent of this window?
It's almost 100%. Maybe 99%. Because there is, it's unlikely to be 100%.
Yeah. So you like when we don't know, like we can get fooled by our own eyes that we think it's kind of almost like 100 or 99%, but if it's ceramic, usually it's in the range of like 85 or
Oh,
88%.
it's so good for
Yeah.
85%.
Even like 85%, like we can see like this
Yeah,
highly
actually,
transparent.
if we cut some of the figure,
Mhm.
we didn't realize there is something.
Yeah, correct.
Right.
Even like we may not realize there is like
Transparent
material.
So could you explain to us here
Yeah, so-
how we get how we call this one? The theoretical transmittance,
Yeah.
like how many percent, right?
Yeah, so every transparent ceramic or material or glass, like it has its kind of maximum transmittance or theoretical transmittance, we call it. And first of all, I want to show you why it cannot be 100%. Why? Like, so let's assume this blue area is
Air. It should be around 1.
yeah, the refractive index around 1, and we have a kind of material, although like just
The ceramic,
assume,
you
like
mean?
ceramic material. So when the light,
It must be having higher, right? Higher refractive
yeah,
index.
correct. Any other object
Should be higher than
yeah, should be
air.
higher than, it has refractive index higher than air or higher than 1. And when the light propagates from air and hit the surface of the transparent ceramic or transparent material, it will be reflected. There will be reflectance, some kind of portion of it, and it will be transmitted after some deflection because it has a different refractive index. Then at the bottom surface of the transparent ceramic, it will be reflected again. So, and then it will, the rest of it will be transmitted. So you see here, there are two times of reflections, right?
Right.
So that's basically what makes transparent ceramic cannot be 100% transparent.
Because it should be like the summary, the sum
Yeah.
of one and the second one.
So we call it like total reflectivity. So we
I
can
forgot the name.
we can calculate this like total reflectivity, and for example this gamma AlON and depending on the wavelength of light, the refractive index of the material can be different also. So if we consider this as a transparent gamma AlON and we put this into calculation, and we get around like 0.4146 and like around 14.6%. So it means that the total refractivity around this number, and therefore
The transmitter is 100 minus
correct,
this.
and we get this 85.4%
Wow.
transmittance, the theoretical one.
So gamma AlON has very high refractive index.
Yeah.
But so far, with your expertise, which materials of a transparent ceramic has the highest refractive index?
It should be besides gamma AlON, I also studied on transparent Yttrium Titanium, and it has much more higher refractive index, around like higher than 2, like
Wow.
2.2 almost, like that.
How about the maximum, like theoretically or experimentally, maximum refractive index?
I don't know for other materials, but I guess it can be like 2.3, 2.4. So usually the highest the density of the material, the higher the refractive index will be.
Right.
Yeah. So
Oh wow.
let's see here the
Gamma AlON application.
Yeah, the application, the most important property of gamma AlON, which is its
Wow.
like mechanical properties, and we can see when
Yeah, look like the glass is broken, but
Yeah.
the gamma AlON in the first figure is still intact. Like
Yeah,
there is
yeah,
nothing bother
correct.
there.
So this is why gamma AlON is, I would say, is the first choice when people want to use for the like blast protection window or like bulletproof window, because it's superior mechanical properties that make it like very suitable.
But I'm also curious, if I would like to apply this one for my home or my vehicle, how about the price difference? Like comparison between the normal glass and the Gamma AlON?
Yeah, right now, that's why it's like in many kind of application and area, like people still sometimes use like layered of glass, but because of like its cheaper price. But you know, when we use glass, it has like lower mechanical property. Therefore, to achieve like certain protection of the transparent window, you need like more number of glass. Right. But when using like Gamma AlON or other transparent ceramic, you can reduce the thickness or the layer of like the windows. So therefore, you can reduce the profile of the like transparent
The thickness
window.
of the total.
Yeah. So that's.
So how about the price?
The
Can you give us
price,
like
I don't know exactly like the price, but
like 4 times or 10 times?
I cannot give any specific number right now, but
Really?
if you're curious, like you can go to the like one of the manufacturer's website, which is like Surmet, like SURMET.
Alright.
So they produce. They're the leading like manufacturer of the transparent Gamma AlON and maybe also magnesium spinel.
Okay.
So you may check, but I'm not sure about like how much higher the price compared to like conventional glass.
More than bulletproof, can you also explain any other properties of this Gamma AlON?
Yeah. So when we use for because of its mechanical properties in any kind of protection, like you know, for helicopter, there will be many debris and particles like flying around. So it should be like has like high scratch resistance, damage resistance, like that. And depending on its use, like it can be used for lens application also.
Lens, right?
Because it has also high refractive index. And
do we have some figure here?
Oh yeah, let's see here, this one.
Oh.
And this one we can see some characteristic of the transparent Gamma AlON here. You see, it has very large band gap energy.
Right.
Previously, we already talked that it should be higher than 3.26 electron volt.
But here is more.
Yeah, so it's
6.2.
more than enough. And it
Isotropic,
has, correct,
right.
cubic structure. And see here on this figure, this is Gamma AlON, and it has maybe around here also. It has the transmission range from like ultraviolet light to the mid infrared light. So the broader the transmission range, the more application it can be used for.
The broader the application.
Correct. And it has theoretical transmittance like higher than 85%, and also since like it has cubic structure, we can manufacture as a polycrystalline, so therefore it can be flexible in terms of like shape and size, not like single crystal materials. And the most important thing, it has superior mechanical properties.
Gamma AlON. Can you mention like how superior it is as compared to, for example, the previous one, Yttrium Oxide or Mg spinel?
Yeah, I have some figures here. Okay, maybe we can talk about that later. But,
sure.
Here, see, like I previously mentioned, that it can be used for like missile domes also. And you know this one?
Is it similar, missile domes?
No, it's not. It's like kind of like like semiconductor etching equipment. And this the window of this equipment, it should has like good resistance to the
plasma.
Yeah, plasma reaction. So Gamma AlON also has potential, I would say, to be used in the like semiconductor equipment because of its like high chemical resistance. And also like as we see for like bulletproof window and armor vehicle window.
Scratch resistant.
And yeah,
Wow.
because of its mechanical properties.
So basically, like, I saw these materials, almost perfect materials.
Yeah,
They are tough, corrosion resistant, even bulletproof, transparent. You know, we know the difference between transparent and opaque materials. With transparent, we can see while we operating, and also we can see what is inside, what happened inside.
Yeah, that's the benefit of using like transparent window instead just opaque window.
Wow, that's nice.
And we can see here, like as I mentioned, when we use.
You talk about thickness. Will
Yeah,
be
yeah.
reduced.
So, like even like with less number of layer of the transparent gamma AlON, you can even like has higher protection level compared to like just conventional glass.
Wow, that's so nice. Like,
And you know, like not only just size, but you know the how much it will be helpful when you have like thinner profile of the like window, because like using transparent gamma AlON, and it's very helpful I think in many applications.
right. Even if we use the car, if the mass of the car will be reduced, the weight, it will also save our engine. How to say? Save our gas, right?
Yeah,
Gasoline and
correct,
etc.
correct.
Also, if we use this material for aerospace and etc.,
Yeah, usually for
Wow.
military purpose.
that is very excellent materials.
Interesting one. And
I hate this.
this is just a simple phase diagram of alumina and aluminum nitride, and just by simply reacting alumina and aluminum nitride powder, you can get gamma AlON in this region. Usually the stoichiometric around what is it, alumina, AlN,
Aluminum nitride
9 to 5, yeah.
9 to 5.
Uh-huh.
So although this one is very complicated one, because it reminds me of phase diagram of some metals, but you are expert here and you explain that we may focus on that area, the right one, where the composition of alumina and aluminum nitride around 9/4, right?
9 to 5.
9 to 5.
Yeah. And by reacting alumina and aluminum nitride, you will we can transform the structure of alumina, which is hexagonal, into the cubic structure of gamma AlON here. So therefore, we can make into polycrystalline, not like single crystal. And you know, because it has superior mechanical properties comparable to single crystal sapphire, it can be alternative because of its polycrystalline like nature. And we can see here the most important property, the strength and the hardness. It is quite comparable, right?
Wow.
With single crystal sapphire.
Even with sapphire, the gamma AlON, which is more easy to be produced, but has comparable properties of strength and hardness.
Yeah, and much higher compared to other transparent ceramics.
Wow, here I feel that now humanity can achieve some level of the brain power. Like we can utilize our expertise to make our life become more easy
Yeah.
by creating this kind of materials.
Yes, correct.
Thanks to all ceramic professor and all ceramic guys. Wow, so many application up to now. But I'm just curious, do you have more application about this gamma AlON?
Oh yeah, that's very.
I'm sure you have.
That's very good question. So let's see here. So besides its
Wow.
mechanical property,
It's optical, right?
yeah, so it can be used to produce white LED also, and we know that LED is like kind of the next or currently already used, but substituting conventional halogen and fluorescent lamp because of like its like high luminescence power and high efficiency, and also long lifetime. And generally, we can make white LED from 3 different methods. First is the use of red, green, and blue LED chips here, like it shown in this figure. And
I think we have a RGB lamp also behind us.
yeah, but
This-
what I'm saying here is to combine all the light into like white light to produce white light. So another method is to use, which is requiring transparent ceramic, is to use like blue LED chip and yellow phosphor. So when we like shine the yellow phosphor by blue LED, then it will produce like this wavelength of light. Then the combination of this wavelength, it will make into like white light.
So the first peak is about violet blue region, and
Yeah,
then the
this one.
rest is more to green light region, right?
Yeah, correct. Until like red. So we know that the white is combination of all the
color.
visible wavelength, right? So and the third one is using not only one phosphor but multi-phosphor. So using different dopings and different materials of ceramics, we can produce different characteristic of the wavelength.
What's the
And-
meaning of multi-phosphors? Do we add phosphor into the gamma AlON?
Yeah, not exactly phosphor, but we usually call it like the transparent ceramic that is doped with rare earth element is as like phosphor, because it can produce like specific characteristic of light. So by using multi-phosphor, it means that not only one type or one material, but more than one material.
For example, what kind of doping we use?
Here you can see this material use cerium triplus
Cerium.
rare earth element.
It's part of rare earth.
And here we can see that it use Yttrium and also but different host or different material.
Yttrium can also be utilized.
Yeah. And let's see.
Oh, actually, I have one more question.
Sure.
So it's about LED and RGB light and etc. But is it the source also, or it's just like kind of the house that would, how to say, that would help the source of the light to generate that kind of LED light, or it is the source of those light?
Okay, that's very good question, and luckily I have the figure here, and
Oh.
we can see here this is a kind of yellow phosphor converted white LED. So you can see the yellow color that is the transparent ceramic doped with like usually like cerium to produce kind of color that looks like slightly yellow, and underneath it there is like a blue LED. So when the blue LED light shines on the
Yellow
phosphor, then you can see here in this figure, this is the wavelength of the blue LED, and this is the wavelength of the yellow phosphor. Then it will be
so the
produced.
combination would
Yeah.
produce white
Yeah,
color.
you can see here the white light.
Wow, right.
That looks slightly yellow, but yeah.
So, Dr. Aiman, nowadays we can see many LED light that can change the color from white. We just the remote control, and then they will change to blue, red, whatever you want. So, is it the same principle?
Maybe not exactly same. I think what you mentioned that is that it may have like different like diode, like blue, red, and like green LED. So depending on like which one you activate or turn on, then it will show different color, and different combination can make also a new different color, so something like that. But here we talk about like transparent ceramic, but not in the form of transparent bulk ceramic that is doped with rare earth element to produce a new kind of light. So Slightly different
Slightly
concept.
different.
Yeah.
Okay.
And we can see here also, besides the white LED application, it can be used also for laser
Like
application.
blue laser and green laser.
So depending on the transparent ceramic hose and also the rare earth dopants, that it can produce many different wavelength of light. And as I mentioned, that transparent gamma AlON has some potential also to be used for this like white LED or laser application. And I've studied and done research on it, and see, this is basically all gamma AlON doped with different
Another rare earth.
rare earth elements.
So we have strontium, lanthanum,
scandium,
scandium,
lanthanum, praseodymium, samarium, gadolinium,
Wow,
RB,
so many.
so many. And only you see, this is the absorbance like measurement, and you can see only these two wavelength that has
specific
in the
specific
kind of
absorbance.
UV to visible region. Yeah, and by this is the transmittance spectra, and you can see by doping with ytterbium and samarium, you can get the absorbance starting from the around like 600 something, or about like more than 400. So, and because of that it can generate
Specific peaks.
yeah, and this is the photoluminescence spectra here, and you can see that with dope with ytterbium it show
Different color.
yeah, like bluish white color, and with samarium it show
Samarium use
red color. So when doped with certain like rare earth element, that it may change the properties of the absorbance and the photoluminescence property.
Wow. You have lots of experiment, and most of them has different color, right? Like red, blue.
Yes.
Do you find new color from this?
Not
Not belongs to the rainbow color.
So far, when doped with samarium and ytterbium, it show red and blue color, and we can see here that
Here it would be very helpful.
yeah, this is the chromaticity diagram CIE, and depending on the like doping and also the like wavelength excitation, and it can show like different color mapping. Like you see here, this is excitation 333 nanometer. It show like kind of blue color, but when you slightly shift the excitation to 325 nanometer, then it will show almost like to white color region. But with samarium, it basically just show red color, something like that.
So up to now, mostly they can generate what kind of color?
For this transparent gamma AlON, so far I've just observed like bluish white or just blue with ytterbium, and red color with samarium. And with other rare earth, it basically just don't show any kind of absorbance or photoluminescence properties.
Also, is it possible to generate like the center one, the white?
Yeah, it's very possible. Like you see here that I almost got like kind of white light, but just look slightly blue here. You see here, right? But maybe with more like study and research on it, then it's possible to produce like white LED using gamma AlON.
So in the next future, you will also work on this one until you find the white one, or?
It's possible depending on the kind of
funding.
Funding projects and other things. Yeah, but basically, yeah, my research area is transparent ceramics.
For the most useful laser, for example, which color it would be more preferable? You saw us like blue and green, but which one is more useful?
For useful, I think it depends on the application. Maybe certain like surgical application, it needs specific wavelength.
Due to the energy?
Yeah, due to the energy, or like for example, like laser cutting also, it maybe require much higher energy. So in terms of color or wavelength, it's very dependent on the
Application.
Yeah.
Okay.
And we've talked about transparent gamma AlON, right? But also I studied
Using another type of
different material.
ceramic. It's called A2B2O7 group.
Yeah, correct. So this yttrium titanate or Y2T807, it belongs to the bigger group of A2B2O7, which is basically like transition metal group that this one is 3 plus A, the A element 3 plus, and the B element is like 4 plus element.
You talk about covalent, how to say? I forgot about this one. It's like the ionic number, right? Like like aluminum 3 plus.
Yeah, the oxidation state.
Oxidation state. Oh my god, I forgot about it.
Yeah. So depending on the kind of elements, it can produce different material. But I studied on this transparent yttrium titanate, and you see it also has cubic structure, and basically it can be substituted with different like A and
As
B.
long as A is +3 and B is +4,
yeah,
right?
correct. And the melting point is quite low.
Oh yeah, as
Compared
compared
to
to another ceramic.
Yeah.
But compared to metal, it's
yeah.
high still.
Yeah, because like alumina around 2000 degrees Celsius, and so it's quite low. But the most important property of this material is
The
its
transmittance.
high density
Density.
and high refractive index, like 2.3.
It's too high.
Yeah,
2.3.
it's much more higher than gamma AlON that we talked previously. And because of its higher refractive index, the theoretical transmittance
Should
is
be lower.
Yeah, because of more reflectance on the both surface.
It was 85 for the Gamma AlON, and this
correct.
one 73.
But because of this high refractive index, it is very potential. So far, it's not being used commercially or produced commercially, but it has very high potential for the high refractive index camera lens, like optical lens, and many other applications also.
What is skin scintillators? What is that?
Yeah, it's like still in the optical application also. It's similar like kind of photoluminescence application. So it produces new light when it's radiated or excited by the source, different source of light, usually like lower wavelength light.
Dr. Aiman, here we talk about yttrium titanate, which have refractive index around 2.34, which is so high. Is there any direct application that can get beneficial effect from this value?
Yeah, so that's a very good question. So because of its high refractive index, then it means that it has like much higher capacity to bend the light, right? And therefore like it is not now used commercially, but it has very high potential to be used as a like camera lens or optical lens application. And we can see here, this is just a kind of simple camera lens configuration, and you see there are many
parts.
Number of lens or parts. And so why there are many number of lens is because it needs to bend the light, and it has many different function. So when we use higher refractive index of the material, usually camera lens like use glass material, but when we substitute with the ceramic with higher refractive index, especially for this yttrium titanate, then it will reduce the kind of distance of the focal length or the number of lens, because it can bend the light more compared to like glass, right? So therefore I would say like it has a very potential to be used for this camera lens application.
Potential means it's not applicable yet, like not commercialized yet?
Yeah, so far as far as I know, it is not used commercially yet.
Because it is expensive, or because another reason?
Maybe I would say expensive, not really, but I would say because it's quite recent development, and yeah, people
see.
still try to fabricate to get the highest density as possible.
I see. So
And
in
see-
the next future, maybe we can bring our like DSLR camera with more compact size.
yeah, it's possible. Even like now we have like kind of mirrorless, although it's not because of the camera, but not because of the change of the lens material, but yeah, it can be even more compact.
Okay, sure. We will wait for that time.
Okay, and let's see, like
Wow.
this is my
I
recent
saw
study.
the logo of our university there.
Yeah, sure. You noticed that, and so I tried to fabricate this yttrium titanate by hot pressing at this temperature 1400 degrees Celsius. Then you can see this after hot pressing, the sample appears like
Black,
and
yeah,
opaque,
not
right?
transparent at all.
So it's because this yttrium titanate has oxygen ions in it, right? And during the hot pressing in vacuum, and because it's in vacuum, the oxygen like
Will be
diffuse
released.
out,
I see.
exit from the perichrome lattice, and therefore it is oxygen deficient state.
But usually they will have some pores inside, right? If a gas will be vaporized.
Yeah, but in this case it's not pore, but more like just the ions like diffuse out from the lattice, but like not pores, just the ions. And so to achieve the transparency, I did annealing in air at around like 800 degree Celsius temperature, and you can see like the progress. after-
Annealing in air. So
Yeah.
here means, is it possible that the oxygen will come again?
Yeah, because of like air contains like around 20 something percent of oxygen, right? So the oxygen lattice will be restored by annealing in air. So we can see that the transparency started to appear here in this sample after annealing for 6 hours, and achieve the highest transparency after 8 hours. And we can see that the transparency start to decrease again after 9 and 10 hours. And also it's related to the microstructure here. When after annealing for 10 hours, we can see some like gaps and like gaps at the
So
granular.
these gaps will cause the color will change the color from transparent to opaque.
Yeah, kind of, and that's because of the over annealing. And we can see that after sintering or hot pressing and annealing for 8 hours, that the microstructure looks quite dense.
Right. So after hot pressing, basically we will not get any kind of transparent materials, and we should wait for annealing
Yeah, in this case,
to restore. You said to restore the
ions.
oxygen lattice,
ions, yeah,
oxygen
to the
ions
lattice, yeah.
to the lattice of
Yeah, that's
the
correct.
materials. Wow, that is very well structured explanation.
Thank you. And you see by modifying the sintering condition of the temperature here, we can get the different transmittance here because of the different density, and also by modification of the sintering time, also we can achieve the highest transmittance of 60.6%. And we can see the relationship between the relative density and real inline transmittance, that it has a positive inline relationship.
So basically, from these experiments, we can find that you obtain like optimum condition. So not only the highest, not always the highest temperature give the
Correct.
best
Yeah,
result. Not always the longer time of
Yeah.
processing would generate the good result, but we have optimum condition.
Yes.
And the optimum condition is like one of the best that can be offered by a scientist, right?
Yes, that's the thing that scientists, engineers like work to always improve their technology, their products.
Right, and then you are having this kind of result, and yeah, some people will also follow your work, and maybe they will have another work to continue.
Yeah. I hope like this transparent ceramic is quite popular, but I would say it is not like the common like research area. So I hope like more people will explore
Interested.
more. Yeah.
Dr. Aiman, you mentioned that this yttrium titanate is not well explored by many scientists, and yeah, I suggest that other scientists may also come and join and to explore more about this. But what we also want to know, how you compare your own result with the result of other scientist group from other country or other lab.
Yeah, that's very good question. We know that this yttrium titanate is not much studied yet, and so as far as to my knowledge, that so far only 2 other studies have been published on the fabrication of transparent yttrium titanate, and we can see here that this is the highest transparency sample of my in my study, and these are others is quite recent, 2018 and 2019, right? And you can see that the transmittance of my sample, the highest is like 66.6%. And although there are other like groups that have achieved like quite high, slightly higher, which is 70%, but also other group also have shown like lower transparency. So so yeah, it can be still like improve to its theoretical transmittance around 74%, 75%.
Theoretically.
Yeah, so there are still quite much room for improvement in this for this transparent yttrium titanate.
Yes, I believe with more time you can get more optimized condition and better result, like theoretically up to 75%. And you did all your work here in Korea, right? During your PhD and like postdoctoral degree. But is it possible also to implement this kind of technology in like developing countries? Developing countries.
Yes, so for this transparent ceramics, specifically for the fabrication, it doesn't require that much advanced equipment, but as far as there is like, you know, kind of the equipments of like vacuum furnace or like gas pressure sintering furnace or hot pressing furnace, like it is very possible to do the research anywhere in this world. So yeah, I think like the equipment of the vacuum furnace is probably the most important
vacuum furnace
for this fabrication of transparent ceramic.
Wow, thank you so much. And if, for example, me or any other of scientists in Indonesia would like to like be involved in this kind of research, is it possible in Indonesia we can find that kind of machine and facilities?
I don't know much in Indonesia, like how available the kind of furnace and other facility, but yeah, they should have some equipments of furnace, I believe, like vacuum furnace or SPS furnace. So yeah, it's very possible to do in Indonesia or any other place.
So today we learned a lot from Dr. Aiman, and still we are curious about the future of transparent ceramic, both in Korea, Indonesia, or even other countries. Could you give us like your 2 cents for this one?
Yeah, so for the future trends or outlook for transparent ceramics, it really depends on the materials and applications, but I would say like in optical, like high power laser cutting or like white LED application, there are still much room to implement or improve the properties for this transparent ceramic doped with the rare earth elements. And also in like defense field, like I think we would expect to see more use of the transparent ceramics in like bulletproof window or the military use, and also maybe for the like in medical field, the use of transparent ceramic for the biomedical imaging. So yeah, I believe there will be still much things
much room.
to do for these transparent ceramics.
Thank you so much, Dr. Aiman, for your excellent explanation and teach us how important it is to develop expertise like step by step and to be contributed to the society. And hopefully next time you can join again to our channel to talk about ceramic, because ceramic is not only transparent ceramic, right?
Yeah.
So until next time, we see you again.